Peter, welcome. Could you tell us in layman's terms what exactly is quantum sensing and how can this be important to biology and medicine?
Yeah, no, definitely. Before answering the question, let me thank for the invitation and organizing this great event. And I'm looking forward to many more to come. So quantum sensing is a really rapidly developing field that allows us to develop new type of sensor capabilities that can probe physical properties at the nanoscale that are beyond the reach of current technologies. And while quantum sensing is part of quantum information technology, like quantum computing and quantum communication, it has, to some sense, been actually around much longer than the other two fields. And a very notable example here is actually quantum metrology, precision measurement of time, in the form of atomic clocks. And I would say that's maybe an area where quantum sensing, quantum metrology already has had a lasting impact on our society. For example, when we came here, at least, I had to find the way, and I used GPS on my mobile phone. And the technology that makes GPS available is precise measurements that allow us to synchronize GPS signals between different satellites, and that needs to measure kind of at the speed of light, basically timings. And so this would never have been possible with conventional timekeeping devices, with quartz oscillators, and really required quantum systems to perform these measurements of times. And so since then, kind of quantum measurement has moved on quite a bit. We can now measure time with 10 to the minus 19 precision. So if I translate that into a unit that is maybe easier to understand, the age of the universe is 14 billion years, roughly, plus minus. And if you switched on an atomic clock, now the best atomic clocks that we today have in the lab, at the birth of the universe, it would now be off by less than 100 milliseconds. And so these kind of advances in precision measurements, we are now starting to actually exploit and apply to other areas beyond time sensing. Sensing magnetic fields, electric fields, temperature, strain, using the similar sort of quantum sensing devices. And over the last 10, 20 years, there has been a plurality of different areas that these kind of quantum sensors could have become potential areas of applications. And so some of the first areas were in condensed matter physics, in microelectronics, in geology, actually. People use these quantum sensors now, which was somewhat a surprising, unexpected field of application. And with increasing interest, there is quantum sensing in the life sciences and in medicine being explored. And that's what my group is actually doing at the University of Chicago.
So you focus on diamond-based quantum sensing. Why diamonds?
Yeah, so our quantum sensors, they use actually the vital element is a qubit, the same kind of element that you have in a quantum computer. And these kind of qubits typically have to live at cryogenic temperatures under very pristine conditions in ultra-high vacuums. Otherwise, they interact with the environment and lose their quantum properties. That's, by the way, the reason why it's so difficult to build a quantum computer. Now, while for a quantum computer, it's maybe not an issue to work near absolute zero temperature and in ultra-high vacuum, for a sensor, that can be a limiting factor, particularly if you want to use it for bio-applications. And so if you look around 20 years ago, defects in diamond were the only kind of qubit system that could be used for quantum sensing. that operate at room temperature. And so it was not that we love diamonds. I mean, I really like sparkling diamonds, but that's not the reason why we chose diamonds. It was really because it was the only kind of quantum system that was operational at room temperature. Having that said, this diamond-based technologies for applications in condensed matter physics and in more recently biosensing has really sparked a global interest. There are a couple of dozen research groups at universities around the US and worldwide that are exploiting this kind of diamond-based qubit sensors. But it has become clearer and clearer that with diamond you actually run into limitations, and it's actually not the ideal system in that sense. And there has been more and more interest in finding alternative systems that are more readily biocompatible. And that's one of the things that actually my group has been putting quite a bit of focus on. And we are in the process of actually wrapping up some work where we are using kind of genetically encodable qubits that could open up a complete new direction of quantum sensor, likely actually in the life sciences replace diamond-based technology. At least that's my hope.
So proteins?
Exactly. So kind of our idea would be, can we encode in a protein the same type of qubit that we encode in a diamond-based sensor? And this was kind of actually a crazy idea 2 years ago. It still is a crazy idea, but it turns out that actually certain proteins can behave very similar to a diamond-based qubit, and that's what we are actually in the process of wrapping up now and publishing in the next couple of weeks, actually.
So as quantum sensing becomes more mainstream, how will this impact the workforce? So what are some of the skills that you already see that are going to be necessary?
Yeah, that's actually a big question that we ask in kind of academia, where we do basic research and education, obviously, frequently. How can we get kind of the workforce that has a deep understanding of quantum technology, able to build new quantum sensors, but then also knows enough about the hot applications in life sciences or in microelectronics or in geology? And this type of workforce really requires a convergence of multiple fields. And I think the University of Chicago is here really in a pioneering role, in the sense that we have had the first quantum engineering program in the country. And as part of the Pritzker School of Molecular Engineering, which not only hosts kind of quantum engineering, but also immunoengineering and materials engineering. And having kind of these three disciplines in one building, in one department, really allows to explore new directions that if we were just only quantum physicists among each other, we wouldn't be thinking of. Like, for example, what I was mentioning about qubit based on a protein. And I think that's something that many other places around the country are starting to do now. Harvard, a year ago, I believe, announced a quantum engineering program. ETH has now a quantum engineering program. And I think there will be many more, actually. UCLA, there will be many more coming out over the next years. And I think those quantum engineering programs will all be at the intersection of physics, applied physics, and chemistry, microelectronics, computer science, medicine. And there is even talk about starting to train physicians, medical doctors, in quantum technology to identify new diagnostics applications. So yeah, it's an amazing time to do this now, and workforce development is really going to be a key element if we want to make this technology to succeed in the long run.
Are there any quantum sensing applications currently commercialized?
Yes, there are. I think we are seeing a quite rapid growth, actually, of new companies and applications that are being identified. There are companies that cater the condensed matter physics area, kind of map out magnetic fields at the nanoscale in hard disks and microelectronics. Actually, two of them are based in Switzerland, interestingly. There is a company in Maryland that is building quantum sensing microscopes for geology to map out kind of the composition of certain rocks. There are quantum sensing companies in Colorado, actually, that use atom interferometers to map out gravitational fields and use that for resource exploration. And with increasing numbers, there is actually on the biomedical side companies being created. There is one in Massachusetts, for example, that uses quantum sensors to develop diagnostic devices that can screen for diseases that would be not detectable with conventional sensors. And I think I would be surprised if in the next couple of years we wouldn't see quite a few more companies kind of popping up all over the world using quantum technology to answer certain problems in medicine and in biology. Actually, my students are discussing ideas for companies now already.
Well, on that topic then, where do you see breakthroughs happening in the next 5-10 years in what fields? What's out there that's going to excite everybody?
Yeah, so that's always a dangerous question, right? Because predictions are always wrong, kind of. And the one thing that I've kind of learned from my time in basic research is usually on the 3-year timeline, you overpromise things. On the 10-year timeline, you underpromise. So there's a good chance what I'm going to tell you now is going to be an underpromise. But I think kind of these quantum sensors that my lab and other groups are developing, they really bring a new capability to the table of measuring magnetic fields and electric fields and temperature. And all of these properties have direct applications in medicine. So I think medicine is really going to be the biggest impact application. So where does magnetic field matter, right? For MRI spectroscopy or imaging, we can image now the human body and find tumors in an MRI device. So we could imagine to use a similar kind of quantum-enabled technology to miniaturize an MRI machine to fit on the tip of an endoscope or a surgical tool, and then use that during surgery to identify is that part of tissue that you need to cut out or not. So I think that's actually more like a 5-year application. So with all the approval, probably it's going to be longer, but we have the technology right now. Further down the line, we could envision kind of these kind of quantum sensors to allow us to perform spectroscopy and detect binding of small molecules to biomolecules in a high throughput. That could be very relevant in the exploration of new pharmaceuticals. And I think that will kind of probably dwarf any application that quantum technology currently has, or maybe even have in the future. And maybe even further down the lines, we could use these nanoscale sensors maybe to detect modification to individual proteins in a cellular contents and use that to understand mechanisms of diseases and prevent diseases even before they happen, so we even don't have to treat them. I mean, these are all very speculative, but I think MRI technologies or lasers, they have had such a huge impact on medicine. And in the first days when people were imaging in an MRI tube heavy water versus normal water. That was nobody would have envisioned that this could help hospitals to identify where tumor margins are. And I think there is a good chance we will see kind of similar applications in quantum sensing for medicine in the next 10 years.
I'd like to open it up to questions from the audience.
So temperature is one of the things we really can measure with our quantum sensors really precisely. In that Nature paper that you were referring to, we actually were able to measure temperature inside of a living cell to millikelvin temperature basic precision, or a thousandth of a degree Celsius precision. And so you may ask, why would we ever care in biology? Within a degree, that's sufficient, but being able to measure precisely allows us to measure fast. And so where could this be kind of relevant? So originally when we started this work, actually even back in my PhD, we were saying biological processes, they produce heat. Could we actually measure metabolomic activities? And it actually turns out, if you go through basic back-of-the-envelope calculation, that the temperature raise from a single cell is actually kind of very small. It's about 10 to the minus 6 degree Celsius, a millionth of a degree Celsius. But it turns out that biological processes, as you correctly pointed out, they are very temperature sensitive. So now maybe we shouldn't use it to measure local temperature production, but maybe we can use our thermometer as a way to couple to artificially induced heating, like laser heating, to control temperature very precisely. And one of the applications was actually studying the development of embryos. And so what system are we using here? So these were C. elegans. These are a small worm that is about 0.1 millimeter in length. And they've been a model organism to understand how you go from a single cell, single egg cell, to a complex organism. And they've actually led to the discovery of programmed cell death. And so it actually turns out that in these C. elegans embryos, cells don't divide just at random times, but they divide in a highly synchronized way. And moreover, the cell division rate is actually temperature dependent. And so suddenly we had a tool at our disposal where we can at subcellular length scale modulate temperature and see how that impacts the embryonal development. So this is an application that we did not have on the radar when we started with this nanoscale temperature sensor. Actually, we had this idea of doing a measurement that didn't work out, or that was biologically kind of irrelevant. But we found this other application that actually had direct applications to fundamental biology. And by now, actually, people also use this technology that we developed to stimulate neurons in mice brains. So it turns out that you can, temperature can modify the electrostatic potential on in a neuron and trigger a neuron. And so, but if you heat it too much, you fry the neuron. So using this type of nanoscale thermometer or microscale thermometer that we developed in that work that you pointed out, people are now able to kind of minimally invasive trigger areas in a mouse brain and use it to understand neuroscience. So the development of these kind of new technologies really is very convoluted at times, and it's very difficult to predict. And as you say, like, temperature is very important for biology, so I guess to some extent we were lucky here. But I think magnetic field, electric fields, measurements will have very similar applications in the future. So in some sense, actually, measuring temperature was the lowest hanging fruit in terms of experimental complexity, and that's why you see on that side already applications in biophysics labs. But I think what we see now is still kind of niche applications compared to what we could see in 10 years from now.
Do you see an application also on the human side, human brains?
Yeah, that's. I have a friend in the chemistry department, and he is actually interested in moving quantum sensors into human brains and or into the human body and use magnetic resonance imaging, MRI imaging, to read out, and that would definitely be an application. Another direction where it could go actually is because these quantum states are really sensitive to perturbation. That means you could have, in principle, very good spatial control over which sensor you want to address. And so by doing that, you could maybe turn a sensor into an instrument to do something. So now we are really getting into science fiction here, but there could be maybe, speaking of theranostics, that could be kind of an application here where your sensor could detect something, maybe in the brain, I don't know, and then trigger a biological process on demand by manipulating specific quantum sensors. And these are still crazy ideas, but actually DARPA just had a call out asking for quantum sensors that could be used to manipulate biological processes. And there are definitely ideas floating around that could use these technologies, but maybe in the 20-year time frame, I don't know.
But it could be, for example, for dementia applied.
Yeah,
right?
no.
Or Lou
possible,
Gehrig's,
yeah.
Lou Gehrig's disease.
Yeah.
Right.
It's. I think we should really be open to applications. I wouldn't know immediately how to do it, but there could be definitely opportunities. As with the example with temperature sensing, I'd be surprised. I would not have thought that embryogenesis would be one of the applications. And here we are and are using this now. I think could be very similar things in neuroscience. It's very difficult to predict. Actually, on the diagnostic side on neuroscience, you often have markers in diagnosing Parkinson or Alzheimer that are at very low concentration levels, and maybe some of these quantum sensors that, for example, QDTI, that's a Massachusetts-based startup company is developing, could maybe be here a system that could allow you to diagnose these diseases before they are clinically observable. And with that, maybe you could start intervention early and have a better prognosis for the development of the disease. So yeah, I think we should keep all this, should remain open-minded and explore all these directions. So we should discuss a little bit more about this later on the more technical side, because we are actually building up at U Chicago as part of a big NSF center an instrument, a nanoscale and microscale NMR sensor that will give us, that will operate at 14 Tesla, which is not an amazing field compared to kind of some of the top-end NMR sensors that you're using in chemistry or in biophysics, but it's still good enough to give you structural information. And so what does kind of a quantum sensor bring to the table here? It brings to the table a very small sensor that can give you spatial information of NMR spectra. And with that, you could think of applications like metabolomics on tissue sections, where you can image different cells and monitor the metabolomic activities and profile as time evolves, or as pharmaceuticals diffuse through this section. You could maybe use it to perform kind of high throughput screening where you could have thousands of different measurement stations in a microfluidic channel in parallel and get NMR spectra of multiple of thousands of sites in parallel. So those are kind of different directions that I could envision for like nanoscale or microscale NMR spectroscopy. And I'd be very interested in actually discussing specific applications beyond that. I mean, my personal take here is this kind of quantum sensing for bioapplications or for geology or any other area requires a very interdisciplinary research team. I mean, my background is kind of in, I did a PhD in physics, but then I did a postdoc in biophysics. And so I kind of speak both languages, but I wouldn't be able to kind of talk about specific diseases like how progression of Alzheimer's is. So it's really important to have multidisciplinary teams working together. And I think we should not restrict to specific geographic locations or specific industries. We need to be open-minded and do things at the global scale. That's particularly important for a small country like Switzerland, of course, but it's also true for the US because some of the instruments that we buy, we get actually from Switzerland because there's just one manufacturer in the world that manufactures exactly that device that we need to do a certain experiment. And so I think science in general is driving force through globalization, but quantum sensing for biology or for medicine or for condensed matter physics or for geology is definitely even more of a globalization driving factor, I would say.
The company in question is also a member of the Quantum Exchange here in Chicago.
That's right.
It's Zurich Instruments. Since it's a Swiss company, we can mention the name.
Let's be crazy for a second here, right? So one of the directions I could imagine is these quantum sensors are true nanoscale sensors. So that means you could measure things, biological samples with very small volumes, which could translate in actually very small concentrations. And you could look at spectroscopic signature, maybe in NMR signatures that you wouldn't see with a fluorescent label. And so you could think of kind of the type of COVID tests that we all got used to. When we feel sick, we do one of these immunoassays, right? But maybe with a sensitivity that is billion times more sensitive and not only screens for one disease, but maybe for 10 or 100 diseases. So I think that could be a really interesting thing because then you could start monitoring your state of health kind of continuously and maybe combine it with machine learning and use your own baseline as a reference to see when you should go and see your primary care physician. So these are crazy ideas out there, but I think those ideas would be kind of enabled by either the ultra-high sensitivity to measure things at nanoscale or with small concentration, and or spectroscopic signatures that are not accessible with, for example, an immunoassay where you just look at fluorescence. So that, I think, would be kind of a killer application that could change the world, in my opinion, and maybe even more so than a quantum computer could. But then there are probably even more interesting applications that I can't think of right now. So it's difficult to predict.
Well, we do have some Swiss wines, so I'm sure that can generate some additional ideas for you tonight. I'd like to thank you very much for this presentation. And,
well, thank you for the